Everyone, if you're here for the music, it's in the back. It's called the Easter egg. I'm sure I lost about almost everybody. But okay, but we got a great show. So people who want engineering, please stay. Okay, so let's go ahead. Let's design a simple greenhouse climate system. Okay, this is a simple greenhouse climate system. All right. Uh, we are going to. So here's a scenario. We're hired by a horticulturist to design a simple climate system for his small 500 square foot house. Okay. He doesn't want to spend a fortune. All right. So this is sort of, we're doing an introduction to PID with the proportional integration derivative systems. It's not, it's just a very brief introduction. It's not like the whole class, because the whole class, you could, like I said, this topic right here, you can get a degree in it. We're just going to do a very superficial definition and just go over some very basic concepts. Okay. Engineering manager says we're going to use a development board of your choice. Arduino, Raspberry Pi, it doesn't matter. FPGA boards, embedded, okay? It doesn't matter because this will do it all. We want to implement a simple linear temperature sensor to the device. There is other temperature sensors that are a little bit more involved. We're not quite there yet. We're just going to do a simple temperature sensor. Okay. Display the temperature reading in Fahrenheit on the console. Okay, so there's some on the console on your computer. Use a dual segment binary coded decimal LED display. We've seen that. I hope you guys have seen that. If you're new here, I will do a small brief tutorial on how that works. Okay, so here's the scenario. When the temperature gets above 75 degrees, turn on an air conditioning unit. Okay, if you got an old one, great. I don't, so I have to use a fan. Okay, so use a fan. If it gets below 68 degrees, it's too cold, we turn on a space heater. So your little thing is, your little sensor will regulate the area around you. It's pretty good. There's other sensors that are better, but we're just going to use a linear sensor, okay, for right now. On the code, use the modification codes for the title screen. I showed you almost every single video has it. I will maybe go over it again. At least I'll put the link in the description so you guys can implement that. And it's C++, so it'd be interesting if you could use it in Arduino. If you do it right, you can use it on anything that is C++. All right. Anyways, let's go ahead, and we also want the data to be stable. We don't want it to scroll down the floor. We want it so it appears stable. It's very important. It's very important for a data capture. And for promotion, we want to use modulation programming on the code. I'll leave a link in the description. I know that's a bit tough. I lost a lot of views on the last one because I might have went a little too quick on the code. That's kind of how it is. But I will try to slow it down. I know that's where people are like, oh, here's a block diagram. So the block diagram shows you what I'm talking about in a visual form. So that's only fair. So we need a sensor. It is attached to your development board. The heater is going to be attached to the development board. Also, the block diagram is going to be attached to the development board. And the dual segmented display, which is going to display the temperature in the room, is going to also be attached to the development board. There's a lot more circuitry in that, but that's for people. For the smarty pants, you guys got to figure it out. Now, for the rest of us morons, including myself, I don't mean to call anybody moron, but I know I'm a moron. Stop the video, design, build, and code the project. I will see you on the next section. Okay, so this is the introduction to control system. This is what we're working on. It's a very big field. It's huge. The mathematics does get involved. And it's a very broad general field. And believe it or not, we're human people have been steeped in this for a long time. We just don't know what it is. So we're going to talk about what is a control system. What are some modern examples of controls engineering? Is AI and robotics a threat to humanity? What is the difference between open loop and closed loop, and why control systems are everywhere? Okay. So a control system is is all around us. So wherever you see the technology, it enables the system to do work without too much human interaction. So it measures automatically and then it controls itself due to the environment. So it can be mechanical, electrical, chemical, even social systems. So in a control system, remember your cruise control will adjust to the speed. So if you set it at 70 miles an hour, it will go 70 miles an hour. And when it goes up a hill, it will adjust the speed, it will adjust the gas to go accordingly. And then it will slow down if it's going down a hill accordingly. This is an example of a control system. One of the most important part of society is the sewage system. The sewage system has it's in checks and balances. There's several chemicals that will dissolve human waste as it comes in, and it will turn it into a water. And there's many controls and balances to make this thing happen. This is a very important part. This is the unsung hero of our society. Without this, there would have been more disease, more cholera. It would have been people would have been stinky. It would have been a very horrible thing. Another thing to look at is the one on the right of that is the Tesla. That's the Tesla where there was an article where someone was falling asleep at the wheel, and yes, that is a control system. That control system is they have sensors that senses their world around them, and it corrects itself when there is an object close to it. So if that car is going, if it's in cruise control, it's going at a certain pace, it will correct itself so it doesn't get too close to a car. It may sense the red light. It will do all this stuff. Now, the simplest and what we're doing is a thermostat sort of system here. This too is a control system. It's a very simple one. It's not going into complexity like the Tesla car or even the state sewage department. This is just if there's a if it gets too hot, it sends on the AC. If it gets too cold, it sends on the heater. All of this, all of these are sort of an example of a control system. There's the e-bike. We've seen that many times. People just don't even seem like they're pedaling anymore. And then there is the control system in business, controls to set stuff at a norm. So this one is a bit vague, I think, but I think people need it when you send in a patient who is mentally ill. Their doctors are trying to correct that behavior. So the feedback that they get from other people is to correct that disturbance. And so that too is sort of it's a social control. This is the medical system that helps IV. So it's all over the place. It's everywhere. We just don't really know what's it called. It's all over. It's all it's in our fabric. Okay, so this is the picture of someone falling asleep at the wheel. I like to show that just to see that it is all around us and it is a part of us, and it's a very exciting field. It's exciting field of AI. It's not necessarily computer AI. I think that's what we're talking about. So um, that is a control system. So this is what I saw not too long ago, living close to the Tijuana River there, where is software AI robots going to do this job? So there is a huge problem that we have, and a problem to have control measures of the dirty river that coming from the Tijuana to the San Diego county. There is multiples of trash everywhere. There could be a sewage control system to regulate all this filth, but at the same time, it hasn't seemed to be done. So, do you see robots picking up this trash? Who's going to pick up this trash? Who's going to create this system of clean water and clean living? Human beings, human beings, and there's a huge market for 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 that type of engineering, and it will help um, everyone around. So where AI is taking over, this is what I see. Okay, this is what I know, and this is what I see. The computer system is 100% AI machine. The computer that we're talking is an AI machine. So to go into computer science and to go compete with people who've been working at Microsoft for 30 years, who've been coding for, 12 hours a day, 5 days a week, and you're coming in out of school, yes, you're going to have some issues. You're going to have some because they just been steeply immersed in AI. A lot of software has countermeasures of of trying to um, trying to have hackers or whatever trying to break into their machines. They've already solved all those problems. So that's a 50-year uh, pro, um, program that's been in process. There's also AI when it comes to artwork. I know there's AI in movies and stuff. It all has to do with digital screening. The digital screening, the AI is taking over. It's unfortunately, but it is. And so you have to basically learn AI if you want to be in the computer field because the coding, the programming, it's no longer that C++ programming. It is turned into something else. It, totally, completely. Where AI has been taking over machines for countless years is the doing manual work, doing this type of shoveling area. There's still some of that going on because you can't get a bulldozer in there or anything like that. But doing massive amounts of that type of work, yeah, you can always get an excavator in there, and an excavator or any type of like a drill, which works by itself, is sort of a control system. Also, where AI is coming over is in the manufacturing, where dangerous, boring jobs are getting faded out. So some of the old jobs, and they went on for a while, where you put in a plate and you just pull on the drill press. Believe it or not, those are jobs that should go away. Those are very dangerous jobs. They're mind-numbing jobs. When I worked at my old job there, I've seen quite a few people that would drill their hands all the way through, and they would bust and they'd come out. So jobs like those that are dangerous, that human beings should not be in, maybe in a coal mine or anything like that. Yeah, those jobs are being faded out due to how dangerous and boring they are. So, like I showed the job before, those jobs where you got to clean up, those jobs are not going to go away anytime soon. Mechanics, car mechanics, those are not going to go away anytime soon. Um, that's my that's what I've observed. I don't think it's opinion, but it could be opinion. So let's move on. So let's talk about what's open loop versus closed loop. And open loop systems is pretty much like a math machine. You put in input, something happens, and you get an output. It's we still use the car that we drive is an open loop machinery. However, the fuel system, like the is not. It's actually a control system. There's computers that control that system. They are moving. They're moving away from. They're trying to get like a closed loop, uh, 18-wheeler trucking industry. I don't know how effective that will be, but that may come into play. But I doubt it. But who knows? I could be wrong. um, that's it close. So you put something like a bicycle, like the drill press, like a shovel, or like anything like even the act of driving the car and you manually using the gas. That is a open loop system. Just the act of driving is the electronics inside is not. but the act of it is actually an open loop system. So what is a closed loop system? Is it's basically it's more complex, but it's designed to use feedback. So like I said, the feedback is the most important thing. So instead of continuously putting an input, there is an event, like you push a button and the machine works. It goes forward and there's a controller, like microcontroller. It could be mechanical. It could be, it could be whatever. There are outside disturbances. For our case, there's temperature. Temperature may go up. If it goes up, then it feeds back. There's a corrective there is a corrective measure. The corrective measure could be a heater turns on or an air conditioning unit, to cool it down or to heat it up. That is basically is to keep everything at an equilibrium. So there's multiple units. These type of systems is also the beginning of robotics and have it to work automatically. Is it perfect? No, it's very complicated, and even what we're going to do is going to be slightly complicated, but it's not going to be as complicated as getting like a full robotic welding machine or something like that. So let's go on. I hope you guys enjoy that, and let's go on to the next section.
All right, so our topic today is called analog to digital converter. Okay, we're going to discuss pretty much all the questions: who, what, when, where, why to the analog to digital converter. Now, I'm only going to cover a very superficial amount because this topic is deep with mind-bending mathematics. So this is a topic that's a very important topic, and it can be kind of this topic is actually we've done the DAC before, but this is the analog to digital converter, which means this is where we talk about sensors. This is a very important topic, and it's a very involved topic. Okay, so in ADC, what is an analog digital converter? It's an analog digital converter. It takes the varying voltage from 0 volts to a maximum of n volts, and it converts the volts to a binary code, so the processor can understand it. So it doesn't understand volts; it only understands ones and zeros. So then the programmer needs to harness this data so human beings, I don't think there's any Nagas out there, but who knows, can understand it. In our case, we're using it to read from 0 to 3.3 volts. There are other analog converters that go from 0 to 5 volts, 0 to 10 volts. That's why it's maximum of n volts. All right, so why is the analog converter so important? Well, for embedded systems, it all depends on input. So maybe we need a light sensor, we need temperature, a microphone, vibration. It could vibration from a person's heart. We need any type of sensors. It could be ultrasonic sensors. It could be humidity sensors. All sensors has to be somehow converted into a voltage, and then from that voltage, it then has to go to into a digital code. Now, how does it work? This is how it generally works. First, there's the analog input. There's scaling. So there's a circuit in there that scales. And then it kind of determines where the 3 volts. There's many things going on because it's not a consistent value. Okay, there's a filter. So sometimes when the voltage goes into the microcontroller and all that stuff, when it's sensing, there's a filter. So there's a lot of noise in there. So there's a high pass filter in case there's some sort of squeaky squelch, and there's a low pass where it's like it doesn't want all the low garbage. So it wants to basically contain all the good stuff in a band pass type filter. The sample and hold circuit is sort of a circuit that uses more of a digital filtering system, and it samples it, and it takes the best value, and then it goes into a switch. This is a this is a switch right here. The mux is a switch, and then the switch is wherever it goes. Then it goes to the analog to digital converter. The analog digital converter has many. It has op amps, and so it determines the value. It converts the voltage to the from the op amp. So if it's the voltage is between, if the plus minus is greater than that, greater than the other voltage, then it'll do a 0. If it's greater than, or it'll do a 1, and so on and so on, so until it creates some kind of off on code. Okay, so it's kind of complicated. It's hard for me to discuss, but just kind of like there's a bunch of stuff that goes in the background. How it works. So we kind of saw it. Basically, what it does, it takes a sample. So as the voltage comes in, it takes a sample, and it takes a sample, and it then shoots the sample to the circuit. The circuit then determines of where it's at. Like I said before, the more resolution the sample has, the more distinct, the more faithfully it can reproduce that phenomenon. So if I'm talking to a microphone, it can sample it. If it can sample it as high as it can, it'll actually sound like a real voice rather than sound like a robot voice. Hello, da, da, da. You know what I mean? So that's how it kind of works. A Nyquist, then it goes into a Nyquist system. So it doesn't sample it. What it does, it speeds up. So this is a sine wave. So anything from we hear from 20 hertz to 20,000 hertz, but then on your CD player back in the old days, when we had CD players, but it was sampled at 44.1 kilohertz, and everything is sampled at twice the frequency to prevent aliasing. Okay, so aliasing is a little bit beyond this topic right here, but it's basically aliasing is pretty much it will mimic a signal, and so it looks like a signal, but it's not a signal. So it's kind of like it has its own, kind of like its own name. That's aliasing. The generic formulas to be used to predict ADC is D equals VI VR times 2 to the n. So it's pretty much the same thing as the digital to analog converter, but kind of in reverse. But it's still the same formula, just arranged completely different. So D is the output value. That's what it produces, all the ones and zeros. I think it's in a hexadecimal code, but you can check me on that. There's the input voltage. That's pretty much going from 0 to 3.3 volts. That's going to vary back and forth. So, like in a temperature sensor, if it's cold, it's going to has a low voltage, and then it's basically going to reach you sort of a lower value. As the temperature sensor say it warms up, it's going to give you a higher voltage, and then there's a scaling that is involved. 2 to the n is the resolution. So that is how many points can go to that wave. Okay, and the reference is pretty much is what is the voltage going in. So in our case, it's 3.3 volts. It depends on what circuitry, but in our case, it's 3.3 volts. But this is pretty much the general formula of how it works, and this is what they're aiming for at all times. Okay, so what is the resolution of the nuclear FR11RE embedded device? What is the reference voltage? I already told you that. If I measure 1.58 coming, what would the D value be? That's kind of good to know. So the value that we have, you can just go to your data sheet. It's the data sheet you need to look at is not the Nucleo, whatever it is. It is the chip. So the chip is STM32 F4111. The chip itself, the development board is just, it's like the arms and legs, you know. We want to know what's in that brain, okay? So the CPU, the operating voltage is, where is it? There's 12-bit DAC channels. There's about 10 or so. And then where is it on the device? So you see how the peach-colored analog in, and then there's like a line in there that says A1 and PA1. It can be A1 or PA1, okay? You can't use both, A2 or PA2. They're both sort of connected the same, A3. I like to use these, A3, A4, A6. That kind of helps me out. I don't, you can use these too. You can use PA5. PA5, you can declare that. So analog out, or analog in, excuse me, analog in. And there you go. Okay, so we had to do a little bit of corrections there. The number 1 is 0x06. That's because I put it on F and G instead of B. It all depends on your perspective, you know. Okay, now before we answer the question is, what do we know about common anode? Common anode is we put the VCC, the 3 volts, in, and now it has to accept. Okay, so as it accept, is the code going to be the same? Well, it's actually not the same. Okay, so, all right, so this is the common anode section. It's not A, okay? So that means when it's off, it's a 1. And when it's on, it's a 0. So let's go ahead, and so that means the decimal point, these all are going to be 1s. Let's just go ahead and do it. Okay, so everything's going to be 1s. So everything is the same, except now we have to calculate it with zeros. So the only thing that has a 1 on 0 is G. Okay. Okay. Let's go ahead and this time let's just calculate it out. Okay. C0. Okay. All right, now let's do number 1. I guess we're going to do the same thing. So BC are the only ones that are zeros. Okay. That means everything else is a 1. Okay, it's going to be F something. It's going to be like F9, I think. Let's see. There you go, F9. Just want to confirm it. All right. And so everyone, you can just go ahead and do it yourself, and I will calculate this stuff out. Okay. A4. That's what I got. Number 3. Okay. All right, so let's go and calculate that out. It should be like B0, I think. Yep. All right. Number 4 is number 4. Number 4 is A, E, and D. I think that's going to be 99. I'm pretty sure. Yeah. Let's do number 5. Okay, E and B. That's going to be 91, I think. Let's go check that one out. That was a bit weird. '92. 92. I was off by 1. If you're off by 1, it just won't look right. So. Mm-hmm. 6. Okay. I think B is it right there. B is the culprit. So B is the 1. That's going to be 82, I believe. '82, that's right. Let's do number 7. Okay, we're almost done. Almost done. So number 7 is ABC. ABC. Okay, ABC. Okay, everything else is 1s. Okay. That's definitely going to be F8, I do believe. F8. So sometimes I like to be super confident, but sometimes I need a calculation device to make sure that kind of helps me out, but I'm pretty sure it's F8. Okay, number 8. Number 8, oh, that's a good one. That means they're all 1s. No, they're all 0s, excuse me. I almost mucked that one up. That means they're all 1s. 7, that means they're all 0s. So that's going to be 9, 8, excuse me, 8, 0. And 9, of course, is E and D are 1s. Okay, and that's going to be 98, I believe. 98. Yeah, 98.
This is the parts list, the parts list right there. There's some okay. It's pretty busy. Okay, so I put a lot of pictures in there. Hopefully that can kind of help out instead of a blank board. So we need one dual common cathode 7-segment LED display. That's that one right there. 2 NPN transistors. Those are 2. 7 33 ohms, but that's not 7, but those are resistors. We need 2 1000K. I was meant to put another 10K resistor, if you guys can spare me on that one. One 100 nanofed capacitor, 2 ZGT 25DA. This device is what makes things happen. This right here is the Incredible Hulk right here. This is this thing right here. We'll talk about that a bit later, how amazing that thing is. I need a heater. Just a plain heater you get at Walmart. I don't know, $30. This is a very cheap AC unit. It's like $150. I don't have one. I'm going to use a fan, but maybe you guys might. A temperature sensor. It looks pretty much like a transistor, so it looks like that. Anyways, so those are sort of what you're looking at. So. I will see you. We're going to do some more. We're going to look at the data sheets, and the data sheets we're going to explain. I'll explain more about the transistors, more about the transistors, the TMP temperature sensor, and the relay. So I'll see you there. This is the transistor NPN switch analogy theory. It's in conventional mode. I think this is a great analogy. So we're going to put these transistors on our BCD LED screens, our drivers. They're LEDs. So the right pipe is the least significant digit, and the right pipe is the most significant digit. So to think of transistors in this type of analogy, think as the flash's job. His job is to turn off and on these valves. That's where he gets a little bit of signal. He's going to turn on these valves, turn off these valves. Okay, so current is flowing to the LEDs to the ground. It's also going over it, but he's turning it so fast that it looks like he's at 2 places at the same time. So the flash is going. He's going to this base, then he's going to this base, he's going to this base, he's going to this base, this base, until it looks like he's at one spot. This is the flash. Now, if the flash decides to take a break, and he puts on his headphones and he's jamming out to Metallica and he's messing around with the bass there, well, he's actually amplifying the signal. He's listening to Ride the Lightning. That's his favorite song, Ride the Lightning. So that's if he's in amplification mode. More on that, not today, but right now he's just in switching mode. He's going to switch the bass on. He's going to switch that one and that one. So, and that's how. This is that's how it works. This is how this circuit's going to work. So let's go to the data sheet on the NPN 3904. That's the one I picked. What you want to look for, at least this is what I want to look for, is the base voltage takes 6 volts. It takes the least amount of voltage at 6 volts. It takes up to 6 volts. We're using 3.3 volts. You don't want to go beyond 6 volts in that on the base. So that's the base, that's the collector. Look at the circuit right. You see the arrow. The arrow is pointing down. When it points down, you want to flow current from C to E. Okay, C to E. That's where the electrical current flows. Think of current as like water, like water valve. And we want to make sure that we don't overburden it. So the base needs a resistor. The collector should have a resistor too. And you don't want to have no resistors on here, because V divided by 0 is, well, it's not really undefined. I'll show you that on the board. It is the limit as it goes to 0. I'll probably do that a bit later. And that's 20 milliamps. So can this circuit, at the worst case scenario, can this little transistor handle the load that we're going to give it? Okay. So also, let's talk about the delay time and rise time, which is 35 to 50 nanoseconds. So that is really fast. It's either 35 or 50. 50 nanoseconds. So that, remember, there is 100 million nanoseconds in 1 second. So take that. I'm not into the math. I'm into the big concepts. I will see you on the board, and we're going to go into more mathematical detail, and we'll see if this little transistor can handle it. I'll see you back. Here. I got good sound going on. We're going to talk about transistor right here. This is a BJT transistor. So we have our transistors are going to use as a switch, and we're going to have 2 of them. But for right now, we're going to focus on one part. So the transistor that we have is as a switch. It's going to the BCD. It's going to this thing right here, BCD, and that's the binary coded decimal LED display. Okay, that's it. So it's gonna light up. We have a base right here, a collector, and the emitter. Our emitter goes to ground. Okay, it goes to ground. That's ground. Our base goes to the microcontroller. Okay. And this right here, the microcontroller it's coming out how many volts? 3.3 volts. That's right. Okay. This is 1K right here. 1K. Now, for right now, for simplicity, we're gonna calculate for one LED. Now let's say that one's on. That's it. So that's gonna come up. Okay, we have an R right here. That R, and then we have a diode. Hopefully I can draw this right. Actually, it's the other way. Okay. And then we have a battery. And that battery is coming from the microcontroller. That microcontroller has 3.3 volts. We discussed that. So 3.3 volts. That diode is a red diode. Okay, it's a red diode. Okay, so let's go ahead and do this. We're going to get the IB current to see. First of all, this is 3.3 volts. 3.3 volts is less than 6 volts. So we already know that's good. We need this resistor in here because this is a current device. It's a current sourcing device. And so so let's go ahead and calculate the IB current. So IB equals, let me get my calculator right here. Okay, so this right here is a Casio FX11ES Plus. This is the best calculator in the world. I call this the R2D2. Okay, so the 3.3, okay, is coming like the 3.3, and then there is the diode. This is sort of a diode right here. This usually has a 0.7 volts drop, generically. 0.7 volts. 0.7 volts. And it's going to be 3.3 volts minus 0.7 volts over our 1K, which is an R, equals, K means 1,000. So let's go ahead and do it. 3.3, all right, minus 1.1, okay. No, I'm sorry. 3.3 minus 0.7, okay. All right, answer 1,000. And that's 2.6 milliamps. That equals 2.6 milliamps. So that's pretty low. That's pretty low. So, and this just to open up the the valve. It opens it up. So that's pretty low. So let's go ahead and erase this. All right, erase this. Okay. Now, at worst, so now let's go ahead and there's a diode. Now that diode we know acts kind of like a battery. So that battery is going in the, since we want it to, okay, so I think it goes the opposite way because it goes against it. It doesn't add it. And that usually that's a red LED has like a 1.1 volt drop. So it goes 3.3. The current is going to flow like this. See that arrow? It's not going to go here. It's going to flow all the way down through the collector through the emitter, kind of like you're releasing the valve. It's not going to go this way. It's not. I mean, if there is, it's very negligible, very small amount. There's a negligible amount of R here. It's very tiny. It's almost like a wire. So we just disregard the R there. Okay, there's the R in the transistor. It's very, very small. And the wires are small too. So just negate that too. So it's going to be 3.3 volts. 3.3 volts minus 1.1 volt over that R was 330 ohms. Okay. Okay. And the ICE is, it's more like an approximation. And it's a very good approximation, by the way. 3.3 minus 1.1. Okay. Okay, so put right here. 330. So that's 6 milliamps. Okay, 6 milliamps. Okay. Let's go ahead and erase this. Erase this. So 6 milliamps if only one thing is on. But we have a worst case scenario if all of it's on. So if all this thing's on, there's going to be all this current's going to flow into this one transistor. Okay. So let's go ahead and erase this. Oh man. When all of it's on, it basically, so your R is connected to ground, right? And it's connected to that. But it's not connected in series. So you have a battery right here and another R right here. And so on until okay, times by 5, 6, 7. Okay, so it's all in series. Your volts will remain the same. It's in series. Okay. I mean, it's in parallel, excuse me. Your R is also in parallel. They all go to ground. Everything goes to ground. Each one goes to ground. So to calculate at the worst case scenario, that's 8. It's 6 milliamps Oh, wait. Sometimes these boards are just a pain in the neck. Six milliamps. Okay, 6 milliamps times 7. Okay, that's 42. I can count on my fingers. 42 milliamps. So our question is, we go back to the data sheet. 300 is greater than 42. Therefore, it'll be fine. Now, let's discuss some stuff about current. Why resistors are important. You should always include So let me erase this a little bit better. When you're designing, putting in a resistor is always a good thing. Because if it's coming from a source, like a battery source, you got your V, and then you got coming from here. And let's say you just have it straight wire there. Okay. And this is a V. I don't know how much that is. So that R is pretty small. So let's say, that would be V over 0 equals I. Now we know that V over 0 is undefined, but in the real world, there's no such thing as like idealistic. So, and I know this is coming from our microcontroller, so it's always good practice. That's not what 0 is. What it is, and I don't care if it's like it could be a power plant, but any type of electrical system, it's V over the limit of the function of I as R goes to 0 equals infinity. So that means the function as R goes to 0, it equals infinity. So that's why you want to put you kind of want to just use just plain old Ohm's law, even if it's a power plant and all that stuff. So it's the limit of R goes into 0 equals infinity. It won't really cause it to catch on fire, but you could damage the device, or you could damage the microcontroller, especially if it's coming from an outside source. Like if this V was a power supply, it's coming from an outside source, that could burn up the transistor. Okay, so I hope you enjoy that, and let's go on to the next section. This is a low voltage temperature sensor. We're doing it could be the TMP36. I hope you guys can all see that, but I highlighted, or I circled in red. There is the 10 millivolts per Celsius. That is a slope. Okay. This is a pinout. So number 1 is the VS. That's your 3.3 volts. V2 is the out. That's where it detects the signal, and 3 is the ground. Okay. All right. So let's go on to the next thing. This right here is a very important part. It's a linear device. Now, it doesn't matter if I had a TMP36, 35, or anything. I'm going to show you on the board how to analyze this correctly. And so you can go to your boss and you can, do almost anything. So on the X axis is the temperature, and the Y axis is the output. So what we want we want a function as the voltage goes in and the temperature comes out in Celsius. And then on the code talk, we'll convert it from Celsius to Fahrenheit. Okay, so I will see you on the board. We're going to take analysis of their chart there. And this is going to just bear me out. We saw there was a graph from 0 volts, and then I pointed out there's 0.5. Those were some of the two most easiest points. So we want to pick the easiest points. For us to work, we also know that I also picked x2 equals 50 and y2 equals 1. Okay, that was on the last video that we just did. We know that there's an M equals 10 volts per Celsius. So if you don't know what that is, remember, anything's per anything. Something Celsius, that means it's going to be a slope. So, which is good. However, the X is going to be, the X right here is our Celsius. So we want this to be our output. So the way this is equation right here, the way it's set up, is not what we want to set. We want this to equal this X in the terms of Y. So let's go ahead and do that. So you go Y minus Y1 equals MX minus X1. MX1. Okay? So let's go ahead and go Y minus Y1 plus X1 M equals MX. Okay. So in terms of, so then what we want to do is take this M on, if you divide the M from here, you want to divide the M from over here. Okay? Divide the M from over here. So that equals 1. Okay? And now we're down to X. Now, X1, that's a good one, right? That's a 0. So that is gone. Everybody see that? X1 is 0 times anything, times the whole universe, is 0. Okay, so let's go ahead and take that out. So now we're just down to this equation right here. Okay. Let's go ahead and erase this stuff right here. And we're just down to right here. X. So X. Okay. Yeah. So X is oh, that's supposed to be, yeah. Okay. So now we have y minus y1. So y minus 0.5 divided by, and your M equals 0.010 equals Celsius. So our Y is volts. So function of V equals Celsius. Okay? All right, so when we turn it into a function, oh, these things suck. I hate these. Turn it into a function, so let's go ahead and take that function of V equals function V minus 0.5 divided by 0.010 equals C. Okay, so I guess we could take it a bit further. Now let's try this again. This is going to be a float. So a float, okay, float, and then it's going to be, we're going to put this, this is going to be voltage, so float V, okay. We're going to return, okay, we're going to return this is void, float V, it's just float V. And, oh, let's call this let's call this math. I'm sorry. Okay, float math or conversions. Does that make sense? Conversions. Okay, so it's going to go in here, and what we want to do is, as it comes in, it's basically we're going to call this float C. Okay, we want to return C, and basically as float V comes in, it's going to be let's make another float V, float C, and so it's going to be V minus 0.5 divided by 0.010, okay, equals C. Got that? So that's what we're going to put in our function. Okay, it's a little bit sloppy, but this is what we're going to put as a function. So it's going to come in. We declare two variables here, or we could just do one. Okay, but it's going to go right here. The V is going to go here, and it's going to convert this into cells. It's going to return that into a float, and we're going to call it conversions. So I'll see you on the next section. Okay, let's introduce to you the solid state relay. This right here, I call it the superhero of all parts. This part right here converts 3 volts into 120 volts AC. This right here makes everything possible. So all you need is a small signal, and these guys right here, you could turn on a lamp. I mean, there's one that says 40 amps and 3 volts to 480 volts. I mean, AC. I mean, that's crazy. So, I mean, that is just nuts. So, I mean, hey, if you want a dimmer switch, right here, that creates the dimmer switch. Okay, that creates what we did, and then you hook that line with the lamp. You got yourself a dimmer. You got yourself a real dimmer switch. Is it, you want to hook? I mean, I wouldn't hook it up to a washing machine. Get it to work. But anyways, this is the other part. Keep that in mind. Look at the stats right there, and let's go on to the next section. Oops. All right, it's time for the AutoCAD section. We got everything going on right here. Now, let's go ahead and talk about it really quick. I know this is very busy. So let's start with the sensor. The sensor, the TMP37, the VO, is connected. This is a capacitor, and make sure it's connected to each other. So these nodes right here means they're connected. If they are going across each other, if they happen to cross, that means they're not connected. It just happens to cross over. Remember that. It gets pretty busy. This symbol right here is the ground. So the sensor is connected to the ground. In fact, this symbol means it's connected to the ground. And the sensor is connected to PA0. Okay, good. I got that connected correctly. So it's filled in. It's connected correctly. And there is a 3.3 volt line going to the sensor right here. All right. So that's the sensor, and that just shows you how it's connected. Now, this is pretty interesting right here. And I want you guys to follow this carefully. This is really quite mind-boggling and also challenging at the same time. So in order to save ports, that's these PC0, PC1, these GPIO pins, some may want to go on a smaller system. This is pretty big, but I wanted to do a smaller system, and this can be done. Let's say you only have 8 GPI pins, or well, let's say you have more than that. 8. Okay, let's say you have 8, 9, 8, or 7, 8, 9, 10. 7, 8, 9, 10, 11 ports. Let's say that's all you have. Okay, that's all you have for GPI pins. To do this correctly, you have to add a transistor on each segment. And how this works is it's going to flash back and forth. So the A is connected to the A. It's shorted out. A is shorted out to the other A. And meanwhile, the A is connected to PC0. Okay. And then B is shorted to B, and it's connected to PC1, C, PC2, so on and so on until you get to G, which is PC6. Okay. However, in order for this to work correctly, PC8 and PC9 must be connected to the 1K ohm transistor right here. This is the symbol for the transistors. These transistors are acting like a switch, and they're switching pretty fast. And so on my other videos, you're going to see it switches a bit dim. That's because there's a lot of the breadboards are not all that great when it comes to connecting. So I highly recommend that you get a soldered into a PCB board. Now, what's very interesting about this circuit here is the PC10 and the PC11. This is connected to these relays right here. It comes in. This acts as a relay. I did this experiment. I just want to be careful. Don't touch these things, okay? These things are hot. They will shock you. And so I just want to put these are pretty powerful little dudes right here. So, and these are connected to the 120 volt AC line. So this has to be on has to be on. The on switch is on. The reason why it's not connected, the reason why it's not on all the time is because this switch will engage when this is ready to. We'll talk about that more on the code. So these relays will determine, and these are connected. This is the 120 volt line. These are supposed to be the plugs. So let me go ahead and go out. Okay, and remember that when there's a node, that one right there is supposed to be a node, but it won't. That's connected to ground. If there's a node, then it's connected to another node, then it's connected. But you see how this is crosses over this? That's not connected. Okay, so just because there's a lot. Sometimes when you look at these schematics, they can be kind of confusing. So how I do is I put some node to node, and that kind of helps out. That helps out trying to clarify some things. So, and the funny thing is, if you do it right, you can have many of these BCD drivers going on at the same time. As long as these transistor switch, you can have up to 4. So that's if you PCB it right. So there's the 330 ohms, and this only works. This is just to limit the current to these transistors right here. So that's where it goes. It goes from here. It goes to the collector. The base this is the base right here. This is where they see how it tees off. This is the base. The base is connected to PC8, PC9. So when this engages, the base will open up the valve and current will flow through these arrows right here. It's quite amazing, actually. It's quite amazing. And it goes to ground. Meanwhile, this will light up. And in a way, it will light up all at the same time, because these things are going so fast that it's supposed to trick the eye. So that should do it for the AutoCAD section. I'm going to go ahead and go out a little bit more and try to get the big picture of it. Okay, so let's go in and try to get the big picture. Okay, and then let's go over here and try to get the big picture of it. Okay, these are connected to ground, by the way, so just want to let you guys know that. See, see, it's connected to ground. Okay, and then let's go ahead and get the big picture, and these are the relays. Okay, there's a disclaimer. Please handle them with care. They're like little superheroes. They'll give you a good punch if you're not careful. And these are connected to the heater and the air conditioner, which is also plugged in. All right, so let's go to the code talk, which is next. All right, so let's go ahead and do this. Okay, welcome to Code Talk. This is it right here, and this is where we sort of discuss the intricacies of C++ programming. This is what have I come up with. Some of this is actually I made up, so this is so it's kind of pay attention to this. So let's talk about the first part. Hashtag include embedded.h. The hashtag modcodes.h, that is mine. I made that one up. Before we begin, we always do a embed.json right here. This is a very sensitive file, so don't put any comments, don't put anything in here. So target overrides with it has to be exactly like this. What this does is it enables the floats to appear on the computer screen. This is not that important in this exercises, but you'll see what it does. Okay, so the next one is we're going to talk about the header file mod codes, and we're just going to talk about what these things do, okay? And then we'll come back to the actual code itself. So these are the mod codes. The mod codes, the clear screen, what it does is when the title screen comes up, it won't it doesn't scroll down, it keeps it still. So what this does is when there's a data comes in, it clears it, and comes in again. So it clears the screen. Okay, it clears the screen, and there's a cursor. It clears the cursor, and it takes it to the address of OX1B. This is the address of your console. Okay, this right here means home, and the home. There's a home screen, and then it goes to this address. Okay, the go-to screen is when you have a constant data. So that constant data, when it updates, it doesn't keep scrolling down. It clears it and then updates again. You'll see what I'm talking about. And there's a cursor, and the cursor will always go to the 01B. Okay. Now, let's go to the main.cpp. Right here there's a lot to declare. And on this, we're going to just show you how the temperature sensor works. You'll see you'll see the strengths, and you'll see the weaknesses also. And so the weaknesses are, well, it's a little bit unstable. And this is this IDE. As you get to more advanced stuff, this IDE is good for basic stuff, but as you get into more advanced stuff, it gets a little bit unstable. And so we'll talk about that. When we're hitting into controls, you're talking about stability. So the stability of this, it works, but it's not as stable as I would like it to be. So there is the LSD enable, MSD enable, and AC unit heater. We'll do that on the next one, but we're just to discuss it. So there has to be these right here. LSD enables the transistors. to flash back and forth. Okay, so here is the float temperature right here. I declare it. This right here, this 4int0, this is a filter. This filter, it does work somewhat. It's not as bad as if it was unfiltered. What it does, it has the data as the temperature goes to the binary coded decimal. It's a little bit more stable, but like I said, this is where this experiment is sort of pushing to the limits of this IDE. Okay, so that's all I'm saying. Here is the transfer function, I guess. This is a linear transfer function, real basic stuff for the temperature sensor. This is to ensure the temperature sensor reads in Celsius, and then we convert the Celsius to Fahrenheit. It's a very basic there, and then returns Fahrenheit as a float, as a floating precision point. Okay, just to be super technical. Here is the title screen. I put the title screen right here. You'll see the title screen. You should be able to see the title screen down below. It says Greenhouse Climate Regulator. Okay, and we're going to uncomment these, and you'll see what I'm talking about if this is your first time here. So the enter the highest point, this is where you put the scan F. The and ampersand high set, that is a pointer. So it has to point to the data. It's not as, it won't point automatically. All the higher level ones, these don't point. You have to force it to point it to the memory address. So the while screen, there's the temperature sensor times 3.3 volts, making sure we have that. And that's, I called the V read. Then this temperature sensor V read right here, remember that this becomes a number, okay? It becomes a floating precision number. So then what I do is I think it's cast, or I put an int right here. This is what this is, casts it. It's into an integer. Okay, it casts it into an integer. Then I filter it again, but all I filter is the least significant digit. When I filter the least significant digit, it does stabilize a little bit, but it still needs some more. So I filter it again, and then it goes to the digits. Okay, so, and then the 1 BCD divided by 10. So if you think of 50 degrees, 50 divided by 10 is 5. 56 divided by 10 is 5. However, 56 mod 10 is 5, 6 as a remainder. So the 6 as a remainder goes into the other digits. Okay? So that's how it kind of works. The temperature sensor is very sensitive here. There's other temperature sensors that are a lot more stable, but this was a very simple linear device. And as people demand for higher quality, you have to get more sophisticated sensors, and they're more of a non-linear sensor. So I just want to tell you, what's going on. For our, this is intermediate, and we'll soon to discover more of a stable temperature sensor. So it goes in here and enables MSD enable. So there's MSD enable. That's going to enable, what that does, it enables the transistor, and it enables the transistor on the binary coded decimal. Okay. And then it waits for 10 milliseconds, and then it enables again. So it's flashing back and forth. Now, what you're going to see is the limits of this device due to the wait screen and trying to print F. It's doing too much. So let's go ahead and see what happens. And you're going to see what happens. And then on the next video here, you'll see this will turn on the heater and turn off the heater. But for right now, I just want you to show you what's actually happening. So let's go ahead and do this. Let's go ahead and compile it. Okay, so I'm going to put in 73. Okay, set the lowest point. I'm going to put in 68. Okay, 68. Okay, you see, that's what it's actually doing. That's what you see. So that's what it's actually doing. You see, it is going to the console, the measure of the console temperature. It's keeping the data stable. It's keeping the data in one spot. The data is not necessarily stable, but it's in one spot. Okay. We're looking at the BCD driver, and you see how it's flashing. It's not too bad. It's flashing back and forth, but this is due to the printfs. I was sitting there just scratching about, like, why in the heck is it doing? Is Flash not doing his job? Well, it's the processor is actually having a heck of a time. It's not Flash is doing a fine job. It's the processor. Now, let me show you guys something, okay? Let me guys show you something which is pretty cool. I'm going to go back to my IDE. You don't see it, but I'm going to comment that out. In fact, I'm going to delete it completely. Just so there's no... And I'm going to compile it. We're just going to have to wait. So go ahead and wait. Okay, I got to put in... Okay, so now I got to put in all that stuff. All right, 73. Okay, 68. See it? So now it's actually a little bit more unstable, but it's now you can see it more clearly. And the second digit still reading 73, but it's not filtering as much. So how is this? Hold on, guys. So you can see it clearly. It's 73. It's very sensitive. 73, 74. Wants to go to 74. 73, 74. Now, believe it or not, that's only hooked up to 6 points. Let me show you how this is cool, okay? So 6 points. Let me see some. Remember, Flash is doing that. He's going pretty fast, and it's pretty clear. Now, let me slow it down. This is really cool. This is what I'm telling you about. Talking about, excuse me. So let me go ahead and do it. Bear with me, folks. It's like a magic trick. I'll show it. Okay, just bear with me. I know. All right, now 68. See it? 73. It's actually very 75, but you see how you can see it's going very slow. Believe it or not, those are the transistors. See that? The transistors are working 1 second at a time. But when I lower the time gets so fast that it looks like it's one thing. This is how movie pictures work. Okay, now it's 72, 73. So let's go ahead and take that down to 60 hertz, which is, I think it's 16 milliseconds. This is the flashing of your monitor. Okay. Let's Try this again. I gotta recompile it because I changed the code up. I changed the timing of it. Okay, and I gotta do all this good stuff. So there it goes. It's compiling. Okay, I gotta do all this stuff right here. And 68. There you go. See it? That's at 60 hertz. And so it looks like it's doing two things at the same time. All right, guys. So let's go ahead and let's go downstairs and let's get to the main controls of it. I'll see you downstairs. Okay, so right now it is 79, 80 degrees according to the BCD. And now let me show you. Behold, the fan is on. Okay, let me turn it the other way. There it is. See it? It's on. Okay, the fan's on. Okay, the light's on. Okay. Now, if I could do this correctly without mucking everything up, I'm going to put the sensor, that's why I got it so long, into the freezer. Okay, into the freezer. If I could just, without disconnecting it. Okay, come on, little freezer. Dude, there it goes. There it goes. It's going down. 69. And there goes the heater. You see that? Now the heater turns on. And now it's going down. Okay. Whew. That's the heater. I can feel the heat. And now the other light comes on. Now it's super hot in here. Okay. Thank you. Stick around. Hope you guys watch the, I call it the Easter egg, when you see at the back of a movie. I'll be playing some music. And I'll see you on the next Engineering Bart Show.